So we've already pre-configured timing commander so we can program the board. But let me show you how the board is set up. So we have the board. It has 3 banana jack connectors, 2 red for VCC, 1 black for ground. So we're going to jumper these together. Now, you'll notice that there is a VCCO jack and a VCC jack. These give the customer the option to power VCC at a voltage that's different from VCCO. For example, they can power VCC at 3.3 volts and VCCO at 2.5. But for this session, we're only going to power it at 3.3. So now we take the banana jack and we connect it to the power supply. But before that, let me show you the power supply setting here. This power supply is off, so let's go ahead and turn it on. And here I've verified that the voltage is 3.3 volts. It's important to power up the supply and verify the voltage because there could be cases where a customer has powered a 12 volt or a 6.5 volt device and the supply might still be configured at that voltage. So now that we've verified that it's 3.3 volts, let me turn it off. I am going to connect the VCC to the power. And the black cable is actually connected to the VEE. So I'm going to connect that on the eval board to the black banana jack connector. The next thing I'm going to do is I'm going to connect the USB cable to the laptop. So it's very simple. You connect it here and you connect it to a laptop. While we're doing this, let me also emphasize that currently, as of April 29th, Timing Commander supports USB 2.0 ports. USB 3.0 ports are currently not supported. However, we will support them within about a couple weeks. So I am going to ensure that the port I am connecting to on the laptop is indeed a 2.0 port. Okay, so at this moment, if this is the first time that the board has been connected to the PC with Timing Commander, it needs a little bit of time to initialize the drivers. One common mistake that users may make is that they connect the board and immediately expect to connect Timing Commander with the board without allowing the time for the drivers to initialize. So I have now verified that the USB port is recognized by the laptop. And what I'm going to do now is power up the board. So let's go ahead and turn on the power. And notice that current is 252 milliamps. Should you see more than that, I would recommend to power down the device because there could be a short. But now that we verified that current is about 250 milliamps, we know that it's in the default configuration. The board ships with a 38.88 megahertz crystal. And what we're going to do next is actually connect the board to the scope so that we can measure the output frequency. So this scope is already pre-configured with a 50 ohm load. So there is a 50 ohm termination on channel 1 and channel 2. I'm going to take the SMA cables and connect them to Q0. So Q0 is the only output that is enabled on the default configuration. And now that it's connected, we have an output of 155.52 megahertz, and that is the default configuration. So now I am almost ready to write the Timing Commander settings to the board. Before I do that, I am going to press reset. So this is the reset button, and that just ensures that we have the correct default settings. All right, so the board is powered up. We verified that the current is correct. We verified that the output frequency is correct. Now we're going to connect to the chip. We do that by using the chip icon on the top right of the GUI. When we press that, a green window appears. That little green box indicates that the board is connected. Now, if you click the text on the top left, there is a monitor that ensures and is every second detecting if the board is actually connected. Right now that's disabled, but if I enable that and now I disconnect the board, you'll notice that the GUI now indicates that the board is connected. So let me go ahead and plug that back in. And I'm going to disconnect the chip and once more connect. And now the GUI informs us that there has been a successful connection. For the moment, I'm going to disable that feature. So Q0, let's configure that for 156.25 LV-PECL levels. Now that I have my configuration ready, I simply press the right button, a GUI pops up, a window, and it says write to attached chip. The UFT++ board, or UFT3G board, comes with two chips. This is the UFT3G board, or device. The second chip that's present on that evaluation board is an EEPROM. But for this demo, we're only going to write to the device. So now I want you to observe the change. Before I do that, let me just add another two outputs so that we can draw a little bit more power. So I've added the outputs. Now I'm going to write all. So write to attached chip. I want you to pay attention to the scope, because when I press write to attached chip, this frequency is going to change. So write to attached chip, write all has completed, and as you observe, the frequency is now 156.25. So let's say I want to change the output level types. Timing Commander allows us to reflect those changes immediately on the chip. So if we look at the scope once more, Q0 is configured for LV-PECL levels. But if I change this level to LVDS, the moment I change it, the scope reflects that change. And so in this case, the trigger level is a little bit offset. So let's center that. And now the scope is reflecting that we have LVDS levels. Similarly, I can switch, for example, to LV-CMOS, and we can see that amplitude changes immediately. That feature can be enabled or disabled. So most commonly when a customer is configuring the device, they'll want to see real-time feedback. And so that feature is actually called write immediate. This button here shows write changes to the chip immediately. When that is set to yes, any changes that affect the register settings will be immediately written to the device. Now there will be cases where customers want to change various outputs at the very same time. In that case, we disable write immediate and use a write all to dump all those register settings into the device in a single step, and so they all happen simultaneously. So one other feature that Timing Commander has is that there are interrupts for the UFT3G board. These interrupts reflect the status, or they're interrupts showing whether a clock has been lost. This board is configured in synthesizer mode. So because of that, the clocks 0 through clock 3 are always going to show an interrupt. However, if we clear the sticky bits, the auto poll is going to show that PLL 0 is actually locked. The current setting in PLL 0 does not apply in synthesizer mode. So in this case, the PLL is indeed locked. One quick note, auto poll is going to provide current status of the interrupt bits. However, every time that auto poll executes, it queries all the registers that are read-only on the device. It loads them into the GUI and updates all the GUI settings accordingly. Because of that, it does eat up some resources. So if you're debugging in the lab, I would recommend disabling auto poll. And if you want to query the sticky bits, you can use poll now, this button, to actually query what the settings are. So let's say you've already configured the board. You can connect it to a phase noise system, measure the performance, and you finally settle at a configuration that looks good. So the final step is to save that configuration. So using this save button, you can save that configuration, and it's ready for your use next time. So next time we use Timing Commander, simply load the configuration, follow the steps that we've shown you here, and you'll be off and creating fantastic timing solutions. So I just want to thank you for taking a moment to watch this video. Feel free to contact us. I'm Steven Gutierrez. My email is steven.gutierrez@idt.com. I would be happy to answer any of your questions regarding Timing Commander or the UFT 3G product family.